Hey there puzzlers, my name is FLEB, and today I'm going to be covering a tray packing puzzle called the Color Cube Sudoku. This puzzle was invented by Raphael Mayers and was produced by ThinkFun, who sent me this copy for free. The puzzle consists of these 9 cubes in this tray, and the object is to pack the cubes into the tray such that colors don't match in any row or column. So for example, this would not work because there's 2 oranges in the same row, but turning it this way, these 2 cubes could fit in there. There are 6 colors in total, so it's kind of like a Sudoku, without the region constraint. The first challenge is just to find a solution, but it comes with a booklet that talks about other different patterns that you can make. If you just start trying to pack these in, you might be able to fit some of them in, but after a certain point, it's going to be very hard to find the right piece that you need. Rather than just trying things at random, there should be some way to think about this puzzle that allows us to solve it, or at least to reduce the number of possibilities. And so today what I'm going to be doing is going over how to find a solution to this by looking at the puzzle in depth and thinking about different techniques that we've learned over the past couple months. Without further ado, let's get solving. In order to solve this puzzle, we need to remember our goal. Our goal is to get 6 colors in each row, in each column, that are different from each other. So there's only a few actions that we can take. Each of the cubes can be placed in a position and then oriented somewhere on its face. That's really the only things we have available. So let's take a look at each of those in detail and think about where we might be able to attack this problem. For starters, why do these cubes have the colors that they do on the cube? Are there any color combinations that are missing? If you think about the fact that each cube has 4 colors in 4 different spots, there's only a certain number of ways that can happen. If you want to draw them all out, you could. Here's what a few of them look like. But you can also calculate how many there should be. With 4 colors that all have to be different, there are 4 choices for the first spot. Then there are 3 colors remaining. Once you've picked that color, there are 2 remaining for the third spot, and then there's 1 color remaining at the end. That gives a total of 4 times 3 times 2, or 24 different color combinations. Now if you take a look at one of these cubes, there's only 6 faces. And the reason for that is that when you turn these cubes, you also get new color combinations. For instance, on this one, there's 4 different color combinations for its 4 different rotations. That's true of any of these faces. So even though there's only 6 combinations on this cube, by rotating them 4 ways each, you get all 24 different combinations. Now to actually prove that, you have to go through and check out all the different color combinations by hand and make sure that there isn't one that overlaps. But in this case, it turns out they're all unique. So what that means is on each of these cubes, all possible color orientations are given. If all possible color orientations are given, that means that in any place where we know we have the colors right, we can rotate the cube around. You might think that this is sort of a useless line of inquiry, but this actually tells us something very important. It tells us that the orientation of the cubes is very flexible. It's not very constrained by this puzzle. So what probably is more constrained is the position of the colors. So let's take the tray away for a second. Can we create 9 cubes, like this, for instance, such that every 2 columns contains the right number of colors? What I mean by that is, if you look, for example, at this last column here, we don't care about the fact that there are 2 yellows in the same column. What we care about is having 2 yellows in the blocks used to form the right 2 columns. So here, for example, we have to switch this one out for a piece that doesn't have a yellow. Let's start with this piece. We know we need to get another blue, another green, somewhere in this, let's say, row. So let's pick out this piece. This also has a blue and a green. And now we're looking for a piece that has red, white, orange, and yellow. That piece is here. Now I'm not caring right now about the fact that we have 2 greens and 2 reds in the same row. I just want to make sure that we have all the right colors in the same rows. Because the orientation is flexible, we should be able to rotate these around later. Can we make 2 other rows like this? If we start with this one, we can find a second piece which goes with it, and then a third piece to form that row. Once again, there are 2 of each color in this row, and we're not worrying about columns yet either. And so that means that by definition, our final 3 cubes also form a row with the right colors in the right places. Let's now take a look at the columns. We know we have 3 rows, where we have all the colors we need in the first 2 rows, the second 2 rows, and the third 2 rows. Let's make the columns work too. For example, in this column we have 3 oranges, so one of these orange pieces is going to have to switch out. We could do this switch, for instance. That gives us 3 greens though. We could switch these 2 then, but that gives us 3 yellows. And we're just going to continue in this way until we figure out exactly what we need. So we have 2 whites, we have 3 whites. Let's try switching these back again. Now we have 2 whites, 2 greens, 2 reds, 2 yellows, 2 oranges, and 2 blues. So this column is all set. Let's take a look over here. Well, we have 3 oranges and 3 yellows, so something's got to switch there. We also have 3 blues, so switching these 2 won't do anything for us. If we switch these 2, there'll be 3 yellows in the last column. So if we switch these 2, now we have the right number of colors in each pair of 2 columns, in each pair of 2 rows. Now we have a lot of colors that are in the exact same column and row, but we have the general position of where the cubes are going to go, which we, from our earlier analysis, we thought might be more constrained. So now let's fill the cubes into the tray. So let's assume that this cube is oriented correctly. How can we fit the other cubes in? Well, for instance, this guy can't go like this because the blue and the greens will line up. So those need to be offset. That seems to work. And for this final one, we need white and orange. That seems to work. Let's get this row in. That's one of a few combinations that will work. You could also switch around the position of these colors. And then this final one requires an orientation of something like this. Let's take a look at this centerpiece. Now, you can't have a red here or there, so it has one red piece which must go in the corner. That green piece can't go there, so let's try to flip it up either to here or to there. That seems to work. Let's fill in this last piece. So we know on the top we're going to have white and orange. We need to get this orange out of the way of this orange. And that seems to work. Let's get this piece here. That's this one. If you look at this piece, we have a problem now. This piece has orange and yellow, which cannot go in the top 2 pieces or the right 2 pieces. So one of these cubes has to change orientation. Now we know we need the yellow on the right and the orange on the left here, so we know we need to split them up. So let's instead put them at a diagonal, like this. Now we have room for the yellow piece in the upper left, and a room for the orange piece in the lower left. Like this. We have one last piece to fit in. All of these are consistent right now. Let's see if we can do it. The white piece must go in the upper left. The red piece must go in the lower right. The green piece then has to go in the upper right, where there's a contradiction. So something's going to have to change. Let's see if we can change as few things as possible. If we put the last piece in like this, these 2 pieces are okay, but now we have a blue in the same row and a green in the same row. But those are the only contradictions we have, and since we can find all the orientations, we should be able to find one with the blue-green here switched, so that if you go clockwise, it's yellow, green, blue, orange. And here it is. Yellow, green, blue, orange. And now because the only thing we switched was these 2, everything else works. And we've found a solution. What happened here is that we had to think very generally about what's going to be flexible in the puzzle versus what's not going to be flexible. And when we did that, what we found is the orientation is very flexible, while the position is not. So we were able to constrain the position and then use the fact that the orientation was flexible to get everything into the grid and find a solution to the puzzle. Thank you very much for watching, everyone. And as always, happy puzzling!